Okay, so next up we're going to talk about compound interest. And this is the only real formula in chapters 6.1, 6.2, and I think 6.3 and 6.4. You will have some formulas in 6.5. So, or not formulas, but properties to remember. At any rate, so if you put some money, we're going to call that A of t, the amount of your money. So the amount of money that a principal, meaning an initial deposit, P, will grow to after t years at interest rate R when we're compounding n times per year is given by this lovely formula right here. So this is like if you put money in a savings account, right, at the bank, they're going to pay you simple interest once a month, right? So if you put in, $100 into the savings account, and let's say they're paying 1%, they're going to pay you $1 over the course of the year. So they're going to pay you 1/12 of that each month, right? And that's really what's happening here, because we've got the interest rate. You're not getting the full interest rate every month. You're going to get 1/12 of the interest rate each month. Okay, so A is your account balance, P is your principal, R is your annual interest rate, but it's in decimal. It'll usually be given in percent, so you do need to change that to decimal. N is the number of compounding periods per year. That's how often you get paid your interest. And T is the time, how many years you're letting the money sit and grow. Okay, this you can also, this is like, if you borrow money from a bank and they start charging you interest, like student loans, and you're not making payments on it because they've given you, a no payment period, but interest is still accruing, this formula is going to give you how much you're going to owe if you don't make payments. Okay, so we're going to invest $1 at 100, somehow, this is just to relate to what E is, right? We're going to invest $1 at 100% interest for 1 year. So how does the balance change with the number of compounding periods, right? So we've got A of t is equal to P 1 plus R over N to the NT, right? So we're investing $1, so that P is going to become 1. We are 100% interest. So this was our P, this is our R, so 100% in decimal is 1. And we're doing it for 1 year, so T is 1. All right, so we're going to say, well, what is our balance if we get paid once a year? What is our balance if we get paid twice a year? So on and so forth, right? And so we are going to do this with GeoGebra because it gets to be difficult math, right? So we're going to say, okay, I'm going to do this. A of t, A of n, really this should have been n because t we set to be 1, right? So the thing we're letting vary here is going to be the number of compounding periods. So we're going to say A of n. So A of n, let's see if this gives us a hard time or not, equals 1 times 1 plus 1 over n to the n. Okay. And so the question is, okay, so what if we get paid once a year? How much are we going to have at the end of the year? We are going to have $2, right? Okay, so so n is 1, and A of n is going to be 2. If you get paid semi-annually, that means twice a year. And in that case, we would say, okay, what is A of 2? That is 9/4. What is the decimal equivalent of that? That's 2 1/4. Quarterly, that means we're going to get paid 4 times a year, right? So how much is that money? If I get paid, because basically if you get paid 4 times a year, you're getting interest on your interest, right? Because you're not going to take that money and run. You're going to put the interest and leave it in there until the end of the year. So A of 4, whatever that fraction is. And what is that? That's about 2.4414. Monthly, of course, is 12 times. And we're going to go figure out what that is, right? A of 12 is going to tell us is a lovely fraction, 2.613. Yep, 2.613. Roughly. Right? Weekly, how many weeks are there in a year? 52. So A of 52 is going to be a lovely fraction. It's going to have to think for a little bit. And it gave us a decimal equivalent, 2.6926. Roughly. Daily, how many days in a year? 365. All right? So we are going to have A of 365. 2.7145. 2.7145, roughly. All right, how many hours in a year? I don't know off the top of my head, right? 365 times 24, 8760. And so how much, if I get paid interest every hour, tiny microscopic amount of interest, what am I going to end up with at the end of the year? I'm going to end up, my dollar will have turned into $2.7181. 2.71. All right. And if we get paid interest every minute, that is 365 days times 24 hours times 60 minutes. And those of you, apparently there's a song in Rent that says 525,600 minutes, right? So 525, 600. And so that's just about continuous, right? So we could ask, hey, how much interest, how much money am I going to have? I'm going to have $2.71.827. $2, go back. $2.71, 8, can't remember, right? 828, we'll call it. All right. And you can even go to the seconds and so on and so forth, but hopefully what you can see, especially if we look at the graph here, is that this has a horizontal asymptote. What is that horizontal asymptote? It is the number E. So E is our, wait, why is, oh, because I already did E. I was like, hold on a second, EXP, because it already gave me an E. I'm like, wait a second, that's not the right E. So I'm going to use EXP to tell it the E, irrational E. And now it's at the right number, 2.718, whatever the heck it is. 2.71828. You can see we were getting awfully close when we were compounding our money every minute. Okay. So we've got that. So this actually is a way to define E, our irrational number. It is the limit of 1 plus 1 over n to the n as n goes to infinity. Y'all do not need to know that. But you should know approximately what the value is, or at least how to find it from your calculator. So E, so the connection here is between our set number of compounding periods per year with our formula there, and if we basically start compounding so frequently that we can think of it as continuous compounding. And when that happens, we have a slightly different model, which you guys may remember from earlier classes. Some people call it the PERT model or the PERC model. No, PERT, P-E-R-T. So here A is we're doing A e to the RT. A is our initial value, so this could be P, e to the RT. R, which should be lowercase, is the continuous growth rate or the continuous interest rate, and T is our elapsed time. It capitalizes. I don't like that. Okay, so when you see the word continuous compounding or continuous growth, okay, that means we're getting interest on our interest continuously all the time. We're using a different model from the discrete compounding. We're using this e to the RT model. Okay. So long as r is bigger than 1, we have growth. And if r is less than 1, we have decay. Because really what we have here is that this is a, and I'm going to write it e to the r to the t is our model. And so we can think of this e to the r is what we were previously thinking of as b. So this is still really ab to the t, right? But e to the r is always positive. So if r is greater than 1, e to the r is going to be larger than 1. So e to the rt is going to be getting bigger and bigger and bigger. And if r is negative, e to the negative whatever number is going to be very close to 0, right? It's going to be less than 1. And so that value is going to get smaller and smaller as t gets bigger, and so we have decay. Okay, so we kind of went a little long on that, so I lied. There's going to be one more video to go through some examples. Yay, examples, right? So we'll do compounding examples.